Hello everyone, I'm Zifan Xie, a PhD student from Huazhong University of Science and Technology. Today, I will present our paper, Unveiling the Characteristics and the Impact of Security Patch Evolution.
Let's start with the basics of patches. The figure displays a security patch. From a high-level perspective, a patch replaces vulnerable code with safe logic. Patch code is also an essential part of the software codebase. As software evolves, patches evolve along with it, adapting to new requirements and potential threats. Here's an example from the top-down project with vulnerability CVE 2015-338. Over time, developers made incremental changes to the original patch lines. We notice another author are modifying it twice after release. Finally, the original author replaced it with a new sanitizer checker. In this example, we define the modifications made to the original CVE patch throughout the software evolution process as patch evolution. Our question is that, is such patch evolution safe? So, what are the potential impacts of patch evolution? There are three main scenarios. First, code refactor. It improves readability and maintainability. In this case, software security remains unaffected. Second, the fixed logic is disrupted. During collaborative development, different developers may alter the original patch logic, potentially introducing new vulnerabilities. Third, the original patch logic is enhanced, such as adding conditions, implying flaws in the original patch. However, downstream software often backports patches in their original form, which could compromise security if refined patches aren't promptly applied. Patch evolution also impacts security detection tools. We examine if it affects two types: patch presence test tools and similarity-based tools. Our study aims to unveil the characteristics and impact of security patch evolution. We built a dataset by selecting 10 popular open source projects and analyzing their commit histories to track patch evolution. Our focus was on examining the frequency, characteristics, and overall impact. For our dataset, we selected 10 popular open source projects, including Linux and PHP. These projects were chosen because they are easy to compile, have a complete evolution history, and are frequently updated. In total, we collected 1 Dolo 46 CVEs and 2 6033 patches. This dataset is essential for understanding the nature of patch evolution. To track patch evolution, we established definitions. Each security patch consists of multiple hunks, which are the basic units of added, deleted, or contextual statements. For patch-related functions, it refers to functions in which a patch hunk resides. Assume a series of commits may modify patch-related functions. For patch evolution, we start by the original patch and iteratively update it based on the changes made in each commit chronologically. This process allows us to capture the evolved versions of the patch over time. Patch evolution involves updating patch high based on modifications from commit time made on patch I-1. There are 4 types of changes for direct changes. These include line replacements and deletions directly affecting patch I-1. The corresponding CLI is termed a patch evolved commit. An example of direct changes is shown on the right. For indirect changes, these are modifications to statements that modify the control or data flow of patch I-1. The figure illustrates an example of indirect changes. Irrelevant changes. This denotes modifications with no direct or indirect relationship to patch I-1. Removal. This occurs when the commit deletes patch-related functions or the files containing them. Patch evolution occurs when a CVE patch undergoes at least one direct change. In our dataset of 1 low 46 CVs, 848 patches evolved. This indicates that patch evolution is prevalent, occurring in over 81.1% of cases. We analyzed modification types, finding that each CVE patch averages 1.8 direct changes, with irrelevant changes being most common at 10.1 per evolved CVE. Next, we analyzed the timeline for patch evolution to understand patch life cycles and management. We focused on two metrics. Initial evolution timing, it denotes the time to the first evolved commit, and average evolution duration. It denotes the time between the original patch and last evolved commit. Our results show that 44 CVE patches were modified on release day, 207 within 90 days, and 161 had an average evolution cycle within 90 days. We looked at authorship changes in patch evolution, as research suggests that more developers work on a single file can raise defect risks. We analyzed authorship changes ratio. It denotes whether the patch evolved commit author differs from the original. For unique authorship distribution, it denotes the number of distinct developers on a patch. Our findings show that 93.2% of CVE patches are modified by different developers after release, averaging 2 authors per patch. This indicates that patch evolution often involves multiple contributors, which may impact safety consistency. We then analyzed code feature changes during patch evolution. We focused on security-related characteristics. We analyzed features like conditions and memory APIs to understand how these features are modified. The figure shows the tokens we match during the evolution process. Here, we show an example of indirect changes in code features. In this evolution, control flow was modified with new conditions. Specifically, lines 212 to 213 include changes in condition, relational, arithmetic, and jump features. The table shows the number of direct and indirect changes. Our findings reveal that condition and relational features are the most frequent. There are 787 direct changes and 8028 indirect changes for conditions, and 126 direct and 9559 indirect changes for relational features. These changes often modify control flow, making patches more robust. We also manually analyze evolution patterns. We identified 2 modification types. Type 1 is adjust code without changing fixed logic. These changes are to improve code quality. This type accounts for 54.7% of cases. Type 2 is adjust or refine patches fixed logic. These changes modify the patch logic, like adding conditions to a sanitizer. This type represents 45.3% of cases. Call. Such changes should be carefully handled since they might break the fixed logic. Patch evolution also impacts the accuracy of one-day vulnerability detection tools. We examine if it affects 2 types. Patch presence test tools, which verify if the binary contains the original patch, and similarity-based tools, which compare the target binary to the per-patch version. To test these tools, we selected 6 projects with 3-in-1 CVEs. We compiled multiple binary versions, including pre-patch, post-patch, and 4 evolved versions for each CVE. For patch presence test tools, we use the false positive rate as metric. This measures how often tools mistakenly identify a patched version as unpatched. Our findings show that as patches evolve, the performance of these tools declines. For example, the false positive rate of pmatch increases from 0.229 to 35 across evolved versions. This is because existing tools rely solely on differences between pre-patch and post-patch versions to generate patch signatures. But code evolution can significantly change the code structure. For function similarity-based tools, we assess if tools mistakenly identify an evolved version more similar to the pre-patch version other than post-patch version. The results show a decline in performance as patches evolve. For instance, the false positive rate for safe increased over time. This is because code evolution causes significant changes in code structure, making similarity values less reliable for detecting vulnerabilities and fixes. Finally, we present a case study showing how patch evolution can disrupt fix logic. The original patch adjusted variable pixel info length, but during evolution, another developer modified pixel info, leading to a heap buffer overflow vulnerability. Using the directed fuzzer AFE algo, we identified this security flaw. The related data flow is marked in the figure. This case highlights the security risks in patch management. We propose 3 actionable suggestions to address security challenges in patch evolution. First, Patch Evolution Sanitizer can help detect if modifications compromise security. Second, enhancing patch presence test tools. This can improve tools by adapting signatures to account for evolution patterns like condition and relational changes. Finally, facilitating patch backporting. It helps downstream developers maintain logical consistency by tracking refinements in patch evolution. These can help enhance software security during patch evolution.
Thanks for listening.